As hydrogen production ramps up, we are leaping orders of magnitude from megascale to gigascale projects. The largest hydrogen electrolyzers operating today are in the 20 megawatt range. Plans already exist for gigawatt systems. Scale up is also the order of the day for hydrogen production from natural gas and coal. As an example, let's look at the H2H Salt-N project that is planned to support decarbonisation of the Humber industrial cluster in East Yorkshire in the United Kingdom. It proposes a 600 megawatt autothermal reactor, or ATR, hydrogen-rich syngas. Conventional steam methane reformers do not require pure oxygen. On the other hand, ATRs do. And to enable 600 megawatts of hydrogen production, about 1,200 tons of oxygen per day would need to be made on an air separation unit. That would be one of the largest ASUs in the UK. Producing hydrogen from natural gas using reformers means that carbon dioxide is generated from the process chemistry and the heat energy requirements. Blue hydrogen is produced through the integration of carbon capture. To qualify for the blue hydrogen label, the captured CO2 must be sent to a CCS scheme where it's permanently stored underground in natural geological formations. From the H2H Salt-N reformer, CO2 will be sequestered under the North Sea as part of the Zero Carbon Humber project. CCS is an established technology in the North Sea. Equinor commenced capture and sequestration of CO2 on the Sleipner West field in the Norwegian sector more than 20 years ago. The CCS scheme, from the absorption tower to the multi-stage CO2 compressor with the integrated drying system, are all highly developed. CCS, or CCUS, when combined with EOR, has also been used in Australia, Canada, and the United States for many years. Most major CCS schemes have been carbon capture retrofits onto existing carbon-intensive processes, such as coal-fired power plants or steam methane reformers. Since they have been retrofit projects, reforming technologies and CCS have been developed in parallel. They have never been optimized as an integrated process. New hydrogen production, a paradigm shift is required. The system must be optimized in a holistic way. Take this example. Downstream of the reformer, some blue hydrogen schemes will integrate blue ammonia production. Like hydrogen, ammonia is a carbon-free energy vector. Use of ammonia as a fuel will expand its range of applications and drive significant growth in ammonia demand. Ammonia production requires nitrogen as a feedstock to react with the hydrogen to make the ammonia molecule NH3. The nitrogen could be produced on the air alongside the oxygen that feeds the ATR. The reforming, air separation, and ammonia processes would be interdependent, and the integrated equipment can be reviewed as a blue energy island. The use of natural gas and air separation units to make syngas for fuels goes beyond their proposed application to make low-carbon hydrogen. In 2006, the Oryx Gas to Liquids project in Qatar was built to add value to natural gas and produce liquid fuels as energy-dense export products. Oryx has 2 ATRs, and each is fed by large ASUs, rated at 3,500 tons per day of oxygen. The 2 ASU cold boxes for Oryx were built by Air Products at Agrafair in Wales and were shipped to the Middle East from Ellesmere Port. In a similar project, the Escravos GTL facility in Nigeria started up in 2014. It's of a similar configuration to Oryx, and it also uses 2 Air Products ASUs rated at 3,500 tons per day of oxygen. Shell's Pearl GTL facility at Ras Laffan in Qatar started up, fed by 8 Linde ASUs that can produce a total of almost 30,000 tons per day of oxygen. In contrast to Oryx, Pearl uses partial oxidation, or POX, to convert natural gas to hydrogen-rich syngas. The use of POX, natural gas gasification technology, for gas to liquids production was pioneered by Shell in 1993 at Bintulu on the island of Sarawak in Malaysia. At Bintulu, oxygen for the POX gasification reactor is now supplied by a 3,200 ton per day air separation unit supplied by Air Liquide. Partial oxidation is like autothermal reforming because the reaction takes place in one unit to which oxygen and natural gas are supplied. But it differs from both the SMR and the ATR processes because neither a catalyst nor steam are used. A subtle difference between the SMR, ATR, and POX processes is the pressure at which they operate. Whilst SMRs typically operate in the range 15 to 40 bar, ATRs are more comfortable in the 30 to 50 bar range, can operate up to 80 bar. If hydrogen is intended for injection into gas transmission pipelines, using it at high pressure is a tremendous benefit because a hydrogen compressor after the reformer can be avoided. This reduces both capex and electrical power demand. This is one of the drivers for the selection of ATRs in proposed gigascale projects if an application of the hydrogen is to substitute natural gas to decarbonize domestic cooking and heating applications.